So now we're live, and yeah.
Be fine. So in times of COVID, it's all about distancing rules, and so it's also about distancing rules for spins in my talk today. And I want to talk about site-specific effects in DNP. So how can we utilize the distance correlation practically between electron spins and nuclear spins in order to derive information directly from DNP? And there are two topics we are talking or we are working on in my group. One is site-specific DNP with localized metal ion polarizing agents. This is where I will talk about today. And the other is so-called screen DNP. We call it like this for specific cross-relaxation enhancement by active motions in a DNP, where we can use SPI groups, practically, or SPI functions, methyl groups, for example, in order to induce an incoherent transfer between protons and carbons. But I will only talk about this at with the site experiment practically. So today I focus about metal ion polarizing agents for site-specific DNP. So when I moved to Germany back from MIT, I had a vision. And so let me first show you my vision from 2012. And this is the basis practically for this whole project. So when we have an electron spin, of course, this electron spin induces different spheres of interaction, practically of influence around it, where nuclear spins are subject to certain interactions. For example, a strong hyperfine interaction shifts nuclear spins completely out of resonance in a certain distance, which is rather short. Then we have a sphere or shell around it where relaxation enhancement is occurring. So nuclei relax faster due to dipolar. You cannot see my screen.
We can see your screen. It's okay. Yeah, maybe you can't see it.
I already got two Q&A posts where you cannot see my screen. So okay, so there's a relaxation sphere practically around it, and then there's.
Wait a minute, Bjorn. Jeffrey, can you see his screen now?
That's weird.
Jeff Reimer says he can see it.
All right.
Why don't you go ahead? All right.
Okay. And then what we postulated is that there's also
your question. I cannot see anything.
So probably I can stop and restart my share.
Yes, please. Now I can see you as a person, I mean.
Can you see it now?
No, I cannot, sorry. I was quite happy with Chris's display, so it's not my computer.
Bjorn, are you using PowerPoint or Keynote?
Yeah, I'm using PowerPoint. Okay. So I can probably directly share the slideshow. Does that work? Can you see it now?
I cannot, no.
Yeah, we can see your screen. Maybe Jeffrey, you want to like log out of Zoom and log in again, because I know that sometimes it solves the problem.
Okay, I will. Thank you for paying attention. I'll log.
All right. So, okay, long story short, the idea is that we have a localized electron spin, for example, an endogenous metal ion, and this would induce a certain interaction around it due to hyperfine interaction. And so if we can use direct DNP, this would be possible then to kind of highlight a certain sphere around the metal ion. And this could, for example, on the one hand, allow us to deduce distance information, but also to simplify, for example, overcrowded spectra. So this was the vision from 2012 and what has become reality in 2020. Of course, there were many other attempts at invoking site-specific DNP. And most of them have relied on so-called indirect DNP, where first the protons are hyperpolarized from an electron spin, and then homonuclear dipole coupling is allowing for very efficient spin diffusion between protons, and then the polarization can spread quite fast, for example, over a molecule, and then it is read out by a cross-polarization pulse, for example. And this causes that even if you attach a polarizing agent label at a protein, for example, the polarization will diffuse all over this protein and might also diffuse onto the solvent or the matrix if there are protons also there. So anyways, there are many different important contributions on this field, some with an endogenous radical. Let me get my pointer again. Some using an endogenous radical, but also some using covalent tagging or non-covalent tagging. So our take on this topic was a little bit different. We thought, okay, we go the other way. We go directly from the electron to carbons without this bipair or relay over protons, and then spin diffusion is very much attenuated. But then the question is, can we still see these nuclei, which are also subject to strong hyperfine interactions, or can we actually use a very weak DNP transfer to nuclei just outside practically this bleaching sphere? One system where we applied this technique to was gadolinium labeled ubiquitin, where we used two different tags, for example, this dipicolinic acid derivative or this DOTA label. And just by comparing these two different linkers, we already see that there seems to be a distance dependence, particularly based on the linker length, where the dipicolinic acid tag is much closer to the protein compared to the gadolinium DOTA tag. And this was also reflected here in line broadening, but also in DNP enhancement. However, the actual enhancement we got was quite small. So I think -3 was the maximum we got. So it's negative because we are operating on the negative solid effect DNP condition, just because we cannot sweep far enough to hit the positive one, but this is fine for us. We still get the same information out. And we measured also that the relaxation time of an unlabeled ubiquitin is just about 10 seconds. So there's a lot of dipolar relaxation, mostly by methyl groups. We were able to improve the situation recently a little bit by looking at a highly deuterated matrix. So also all the exchangeable solvent protons were deuterated. And with this, with the DOTA tag, we also got enhancement of about -3. But if we now compare two different labeling sites, for example, this A28C labeling, and I will show you this the position in a moment, and we just compare this to the G75C position, then we see at the G75C, there's practically no enhancement measurable. In fact, we actually kill our signal completely by just reducing practically our NMR intensity to baseline by not fully inverting. And the reason for this difference is that A28C is situated here, right at this alpha helix, so it's really close to the core, whereas G75 is the second to last amino acid in the C terminus. And this is rather flexible. So this gadolinium tag can adopt a really flexible conformation and can stick out away from the protein. So the distance here is much, much larger. Our most likely culprit for this low polarization is, besides practically the larger distance, also the dipolar relaxation of carbons by protons, most likely in methyl groups, because even at 100 Kelvin, they can still do this threefold hopping. And ubiquitin has quite a lot of methyl groups. So in order to investigate this further, this dipolar relaxation, we looked at a model, and our model here is methionine. And in methionine, we have a really mobile methyl group. And we've already shown that we can nicely probe the cross-relaxation propensities practically in this methyl group by so-called screen DNP, where we use practically the nuclear Overhauser effect under DNP conditions in order to get this very specific cross-relaxation enhancement. And we can see here that by looking at different isotopomers of methionine, we get practically the same cross-relaxation rate or efficiency as long as we have at least one proton in this methyl group. Only if we get rid of all the protons in the CD3 isotopomer, we get rid of this cross-relaxation mechanism. And so we know, okay, when we want to get efficient DNP, we have to get rid of this dipolar relaxation mechanism. That means we have to substitute all methyl protons by deuterium. This is quite difficult because even if you overexpress ubiquitin from a fully deuterated expression medium, where we have achieved an 89% substitution of deuterium of protons by deuterium, we still have about a 40% chance of each methyl group to carry at least one proton. And this reduces our achievable enhancement to about -10 if we utilize this highly deuterated ubiquitin. But nevertheless, we can fully recover practically our negligible DNP enhancement here from the protonated sample and get quite sizable enhancements, but still -10 is not where we want to go. So what about 15N? So I was discouraging my student, Jörg Heiliger, who has done all the DNP experiments, to look at 15N for a long time, because I always said this takes too much time. The build-up times are too slow or too long. The sensitivity, the inherent sensitivity will be too low, even if you compare this to the carbons. So just don't waste any time of that, because our measurement time was always limited. But he was pushing for this, and this was really good because we finally got really nice enhancement when we look at 15N directly. And you can see here, for example, for a 90% deuterated expression medium, we get an enhancement of about -100. So we get a quite nice NMR spectrum without cross-polarization in about 30 minutes. And this is from a, I think, a 1 micromolar sample. Sorry, 1 millimolar. That doesn't make any sense. Whereas if we look at the fully deuterated sample, we were not able to measure an off signal without microwaves. So we were not able to quantify our DNP enhancement, but we estimate it's on the order of about probably 400 or -400. So now we actually do see side chain resonances. And from these side chain resonances, we got the idea. So first we thought, okay, forget about carbons. So nitrogen, this is the way to go. This is where we should focus on. And from these side chain resonance, we can now try to look and see if we can determine any distance correlations, for example, by looking at different newtons and different labeling positions where gadolinium is sitting on different positions, and then we can use a kind of a triangulation approach. So now I will spend a few minutes on the theoretical distance dependence. So the theory behind this is not too complicated, but I still want to walk you through because we do find some probably non-intuitive results here. So if we start from the kind of master rate equation, where you can follow practically the polarizations of all the spins in our system by looking at a rate matrix, so a transfer matrix practically, and a relaxation matrix, and we apply this just to this 1 electron, 1 nucleus system relevant for solid effect. we can look, for example, at different relaxation scenarios where we have no nuclear relaxation, but infinite electron relaxation. That means our electron spin, shown here in red, is always maintaining maximum polarization, so 660 if it was a proton, for example. And the other nucleus can kind of creep up here and attach or attain actually the maximum theoretical enhancement. And then we just arrive with this exponential buildup equation. And you can see here this PE naught over PN naught is practically just the ratio of the gyromagnetic ratio. So we can also rename this and call this the maximum DNP enhancement, which is possible. So 660, for example, in the case of a proton. But in our case, of course, we have to assume also nuclear relaxation. So we have this additional relaxation term here, and this causes a reduction of the maximum attainable, or the steady state enhancement with respect to the maximum attainable enhancement, so the theoretical enhancement. So this is the situation we have to look at, and then we can also substitute these factors or these ratios here by the actual instantaneous enhancement factor. Or if we look at the steady state solution where we have no change in our time dependence, so this is the plateau practically, we have here the so-called infinite time enhancement. In this equation we can express as this steady state enhancement, and we can see that this depends on this equilibrium DNP constant, and this is practically a ratio between DNP buildup or DNP transfer and nuclear relaxation. So this is really an equilibrium constant practically. So let's keep these two equations in mind, and let's keep also this kind of master rate equation here. So now we have to look at what are the actual DNP transfer rates. And for this, we look at the fundamental solid effect theory. So we have a static solid effect DNP Hamiltonian. And from this, we can determine that the hyperfine interaction is, of course, the term which connects the electron and the nuclear spins. And this hyperfine interaction, of course, scales with the dipolar coupling constant. And this in turn is a function of the inverse cubic electron nuclear distance. So this is rather simple. Now we have to look at the DNP rate constant practically, and we find here that the transition moment in the end is, of course, also a function of this pseudo-secular hyperfine interaction. So this also scales with the inverse cubic electron nuclear distance. From this, we just evoke Fermi's golden rule, and we see that the important thing here is that the DNP rate constant is a function of the inverse 6th power of the electron nuclear distance, because the transition moment is squared practically in Fermi's golden rule. So this is the next equation we have to keep in mind. So we put this in the other corner. And now we still need the nuclear relaxation. And this is a little bit more complicated because here we have a dipolar relaxation rate and what we call a diamagnetic relaxation rate, which is not affected by the electron spin, but is an intrinsic spin lattice relaxation rate practically of the nuclei. So this is not a function of the electron nuclear distance. The dipolar relaxation rate, we can just utilize Solomon's equation, for example, and then we end up here with this, this dipolar relaxation rate, which is also a function of the inverse 6th power of the electron nuclear distance. So now if we compare these two, and if we put these here in this DNP equilibrium constant, we see that as long as we assume that this dipolar relaxation rate is dominating over the diamagnetic relaxation rate, which is a rather good approximation, then we see that we just have this ratio between the DNP rate constant and the nuclear relaxation rate, or the dipolar nuclear relaxation rate. And this, of course, will lead to complete cancellation of the distance dependence. So in the end, this DNP equilibrium constant, which here determines our steady state enhancement, is completely independent of the electronuclear distance. And this is also a result that Michael Leskes has recently published in doped crystalline lattices, where they found the same result. So the DNP enhancement factor is a really bad measure for the electronuclear distance. All right, so what can we do here? So how can we utilize the electronuclear distance for measurements practically by DNP? If we look at the initial DNP buildup rate, so we analyze this equation here at the initial time point, so t equals 0, then we find that this initial DNP rate only depends on the DNP rate constant and not on the relaxation. And now we have here practically our distance dependence. If we start from thermal equilibrium, we have the ideal case, but usually we don't start from thermal equilibrium in a DNP experiment because this would have us to switch on and off practically our microwaves all the time. So we have to switch them off, wait until the system is equilibrated in thermal equilibrium, then switch it on and quickly measure practically the buildup, which is really non-practical. So what we usually do is we do a full nuclear saturation by a saturation train, for example, and then we measure our buildup. However, this introduces here a contribution from the nuclear relaxation. However, in most cases where we say, okay, our dipolar contribution dominates this overall nuclear relaxation, so this diamagnetic is rather small, then we see that those two contributions here both are a function of the inverse 6th power of the electronuclear distance. So this still is a good measure for the electronuclear distance, and we can neglect this because this is much, much lower than the sum practically of those two components. And in this case, we finally see that indeed we have a measure practically for the electronuclear distance. For example, if we measure here practically the slope, the initial slope of the buildup curve, we see that if we vary R1n, and then vary practically the electronuclear distance, we see that for 3 different distances, this initial slope does not vary. So this is a good approximation. And if we vary kDNP and keep the nuclear relaxation constant, then we see, okay, we can really nicely distinguish these 3 different electronuclear distances. All right, so now back to experiment. Everyone who has went for a coffee during the theoretical slides should now be back. So the take-home message is we can utilize the initial DNP build-up rate practically as a measure for the electronuclear distance. And this is practically the first result we got when we indeed measure practically our DNP enhanced 15N spectra, so direct solid effect to 15N, and only give the system 10 seconds of time, which is a very tiny fraction practically of the full buildup time constant. Then we see significant differences between different labeling positions. For example, if we compare this, sorry. If we compare these 3 spectra here for the 3 different mutants with different contributions or distributions of different amino acids over the protein, we see that, for example, for F4C, the lysines are quite strong initially. And we see that the lysines are clustering around this F4C residue here. Whereas for G75C, we see the arginines are really strong initially. And we see here that the arginines are also clustering mostly around the G75C terminus. And for A28C, the situation is rather in between. If we give the system a much longer time, 512 seconds to equilibrate, everything is much more uniform, and we kind of lose this distance information due to spin diffusion. So we can measure practically the initial buildup, so we don't have to measure this full buildup period over several hundreds of seconds. We can just measure the first 20, 30 seconds or so. And if we do this, we get this distance information without having to measure any enhancement factor. And this is an advantage because enhancement factor always needs the acquisition of an off signal. And the off signal takes a tremendous amount of time. And often it's just not possible. And it's much faster than we don't have to record the full build-up curve, which I've already mentioned. So we don't have to go into the equilibrium practically and the full steady state. So now we have this kind of nice model system, but how can we actually quantify this? So we want to really measure distances, or at least use these DNP information to structurally model practically our protein. So in order to look into this, we started a collaboration with Björn Corzilius due to a very lucky coincidence. We got in contact with him, and he was keen on taking this quite challenging project. And what he did is he first built a conformer library of the gadolinium label, so the Malemido DOTA tag. He generated a library of all the different rotamers practically from which were deposited in the crystallographic open database. And from this, he generated practically a relaxed protein model. And so from this, we were able to project practically the different conformers and the space where the gadolinium can be positioned. And you can see, for example, here in the F4C, gadolinium conformers are much more restrained. And we see this kind of umbrella-shaped space. In A28C, we almost have this half spherical dome. So it's already more, it's more degrees of freedom to orient itself. And in G75C, because we also have the flexibility of the C-terminus, the gadolinium can take up a very large space practically. And we have to account for a lot of different conformers in our inhomogeneous ensemble. So now how can we correlate practically these conformational spaces with our DNP rates? So here you can see the different computationally generated distance distribution. So this is really the distance distribution from each, from the gadolinium in each mutant to the specific amino acid side chain. And here you can already see that different amino acid types have quite different distributions with respect to the different mutants. And this should be possible now to correlate this with our experimental data. So first we had to see if these models were actually representing the samples quite well also in practice. And for this, Tobias Methyl and also Ernst Settiner from the group of Harald Schwalbe in Frankfurt, also teaming up with Georg Künze, and they compared PRE data from HSQC spectra with the models. And here we see a quite good correlation. And so we are quite certain that our computationally generated models really correlate well with our sample conformer distribution. However, when we plotted the measured initial DNP rate versus the computationally generated distance distribution, this was quite disappointing, because when we tried to fit this with our theoretical model, we saw a correlation, a fitness practically of negative 0.028. And this negative sign practically indicates that this correlation is worse than, or this fit is worse than if there was assumed that there is no correlation at all because these two measures. So this led us to, or led me to a lot of thinking and head scratching and looking at the data from different directions. However, at some point we figured out that if we look at these distance distributions, we find a lot of gadolinium or labeling site amino acid residue pairs practically, where our distance distribution extends very much into the really short distances. And at these short distances, we assume that, or we have to assume that there is a lot of signal bleaching going on. So, and this is a quite worse situation, or a really bad situation, because of the r to the -6 dependence of these distances to the final ensembles. The weight practically, the statistical weight of these conformers is much larger than of the conformers with longer distances. So we over exaggerate practically these distances, or these conformers where we do not expect to see them actually. So we have to just exclude those, and for this we tested different bleaching radii. So what we did is we just cut off practically, or we introduced a cutoff distance where we did not include these pairs in our statistics. And then when we tested different cutoff distances against each other, we found that a 12 angstrom cutoff causes a much better correlation, and actually the best correlation in our case. So these two models here just assume contribution from this histidine, which is rather error prone. However, this does not change qualitatively in our result. So now we have to revise here our model, because we have, this was the kind of 2012 vision, and now we know much better. We know on the one hand that PRE and DNP have the same, of course, it's quite obvious now in retrospect, have the same distance dependence, so they always go hand in hand. However, DNP still works even if there's significant PRE, because we weight practically our DNP rate with the theoretical enhancement, and this is 6,500, for example, for 15N. So this works really well for the low gamma nuclei. And bleaching, in our case at least, is expected to act up to 12 angstrom, and we lose practically all the conformers where this pair distance extends practically to smaller distances than about 12 angstrom. So you can see here there's a lot of labeling position amino acid residue pairs practically where the distance distribution extends quite far into these short distances. All right, so this is practically my conclusion slide. So in the beginning, this is the first correlation I've shown you, where we assume that there is no bleaching, and of course this doesn't make any sense, because we would have to look at this picture here. So we have, of course, to introduce our bleaching, and then everything falls practically in line, and we can extract our correlation here. All right, let me thank several people. So the major work was done by Jörg Heiliger, and this was practically his PhD project, and he has shown quite large stamina here, and this was a really challenging project. I also want to thank collaboration with Harald Schwalbe, especially Tobias Matzel and Aaron Cetina, who were involved in the protein expression and also the PRE experiments. Georg Künze was practically life-saving for this project because he developed this protocol of generating the conformal libraries for the gadolinium DOTA and also relaxing the models with MD and other relaxation or other structural methods. And without him, practically, I think this project would not have worked out the way it has, because we would have not been able to make this quantitative correlations. And I want to thank you for your attention, and I'm happy to answer questions.
Okay, Bjorn, that's really a nice, a nice set of results. Could you go back to your last slide where you have so the error bars are, what are the error bars on your distances? You have error bars on your DNP rates, but not on the
yeah, the error bars, let me think, they are quantitative, and they are the error bars from the statistical analysis of the fit, practically, of the built-up curve.
No, yeah, but what is, you know, if you're a structural biologist, for example, you would want to know what is the error bar on the distance measurements.
Okay,
that you.
I see your point. So what we cannot do yet is we cannot measure de novo distances by absolute rates, for example. For this, we would have to introduce some kind of ruler, or we have to calibrate practically our measurement system first. So what we can do here is we can practically use our data from different labeling sites. If we would not know the structure of ubiquitin, we could use this data, for example, as one would do also with PRE data to validate a model and generate a structure, for example.
Well, that would be important at some point to incorporate that into the to the methodology. Okay, so let's so there are 2 or 3 questions already. So from an anonymous attendee, why does the spectra change for gadolinium A28C ubiquitin? Is it due to differential enhancement of different sites?
Yeah, that's a very good question. I have not mentioned this too much. Let me go back to this. So I think this refers to, yeah, to that slide, but without the, so I think this refers to this slide here. Oh, it was A28C.
A28C, yeah.
So I guess this is between the 2 different labels. So I guess this one here. I assume that because the gadolinium here is much closer to the protein, we see more paramagnetic broadening. Also, the relaxation of gadolinium in this ligand and in the DOTA ligand is different, which could have an effect also on the broadening, for example, on the nuclear resonances.
Okay. I guess Jeffrey was able to actually watch your slides because he asked a question. Are distance distributions not dramatically affected by packing effects in solids?
Yes. I have not mentioned that, and that's a good point. We are working in a frozen solution. That means we make sure that the gadoliniums and the proteins are substantially removed from each other, not the gadoliniums and the proteins. So the gadolinium labeled proteins are substantially removed so that there are no intermolecular interactions. This is why we usually work at sub-millimolar concentrations, typically about 500 micromolar.
All right, and Daniel Lee wants to know, since lysine 148 has no short distances, did it fit without requiring a cutoff?
Okay, good question. We cannot measure individual amino acids yet because we don't have single site resolution. This is one problem of biomolecular DNP, that when we have a more or less uniformly labeled system, or a system, yeah, it's uniformly labeled, that we don't have the resolution yet to distinguish different lysines. So we look at the average contribution of all the lysines, and we analyze this in our statistics, and we correlate correctly the average contribution of all the lysines with the average ensemble, or the weighted ensemble response of our model.
Yeah. Okay, so Fred Mintic has raised his hand. Fred, do you want, I think you're unmuted. Do you want to ask a question or something?
Yeah, I have a question. So I wasn't able to read your paper yet, Björn. How are you?
Good, thanks. How are you?
But I have just, so about the I would say the cutoff distance you found, like, if I'm correct, that was 12 angstroms. Do you think that would be dependent on the radical you're using? For instance, you're using gadolinium, therefore you have an effective hyperfine, which is greater. Would you see something different if it was tritium?
Yes, so it should depend on a lot of different parameters. For example, it should most probably depend on the MIS rate. So this is quite interesting because the secular hyperfine interaction, which shifts practically the resonance out of the typical NMR window, could be in theory completely spun out by magic angle spinning, whereas the pseudo-secular has components which are not aligning with the magic angle. So even if you have infinite MAS rate, practically you should retain some pseudo-secular hyperfine interaction. So this is one thing we want to investigate in the future. How does this affect, or how does this evolve practically at very fast MAS? It should depend on the relaxation, for example, and the zero field splitting of gadolinium. So we should make sure that we have the same label, of course, in different labeling positions, so that most likely the relaxation time should not depend so much on the labeling position, but only on the local geometry practically of the label. Different metal ions, of course, would have different effects, and nitroxides even much more different. This is why we still cannot determine the absolute rates, or we use the rates practically to determine absolute distances yet.
So what I was thinking when I looked at your results is you had this problem because of broad distance distribution of your spin label. If you were able to have tritial spin label, you may have been able to avoid this cutoff that you had to use.
Sorry, tritial spin label?
Yes.
Yes, could be. We would have to try.
Annoying chemistry. It's annoying chemistry, that's for sure. But it's just a thought when I saw your results.
So I mean, one thing is having a more narrow distance distribution. The other thing is that we still would have to have a cutoff.
Okay, so Daniel Lee has another question: does the cutoff depend on the mass rate? You may have answered that. And a cutoff of 12 angstroms is about 5 kilohertz for an electron N15 coupling.
Yes, I saw this, but I think this is still anecdotal because we saw this one data point. So we did not really integrate this into the manuscript yet. But this is definitely one thing we have to investigate, yes.
And the final question here is, how do you separate cross-relaxation effects from direct DNP effects for small enhancements, i.e. short distances? and or short distance. Yeah.
Okay, yes. Okay, this is one thing one has to be careful that you might see contributions from cross-relaxation. For N15, this has been shown by Henrike Heise, for example, that ammonium groups, so protonated amino groups, can also show this cross-relaxation. However, the activation barrier is significantly higher than for methyl groups. So usually this only occurs at elevated temperatures. So we think that we don't have these in ubiquitin yet, and we see that the one measure could be that we measure practically the relaxation rates and compare those with the DNP. So as long as we don't see anything practically without microwaves, we can be quite certain that if the relaxation is so fast that cross-relaxation would be involved, that we would not be able to see any direct DNP also. I'm not sure if that made sense what I said now, but the point is that if we have cross-relaxation, this whole thing, of course, would not work.
Okay, well,
but
that
just one thing here. We are using gadolinium, so point number one is the proton DNP enhancement is much smaller than N15 and much smaller than what we see with amopor. So it's usually on the order of maximum of 10 or something like this. And we are not sitting on the proton solid effect condition. So we only see would expect a negligible proton DNP enhancement in this case anyways.
Okay, all right. Well, that concludes all of the questions and answers. And so I think we want to thank again both speakers, Chris Juraniak, as well as Björn Corzilius, for really wonderful talks today. They've introduced to us two new areas that people have not talked very much about in the DNP community previously. And I'm sure we'll hear probably more about both of these topics in future presentations or at meetings, if we ever get back to having meetings again, in-person meetings. So again, thank you very much, Björn, and also thanks to Chris. And we will see you guys hopefully in 2 weeks. We're negotiating the program for 2 weeks from now, and we'll let you know what's going to happen at some point in the very near future. So thank you again. And next week, there will be a tutorial educational presentation at the same time, this station, so to speak. And in 2 weeks, we'll be back here with some more DNP and solid state NMR. See you then. In the meantime, take care of yourselves.
See you. Thanks, Bob.
Bye.